this is a joint work with my student, which actually sit there, Thanadon Kongkoom. And so how to move actually, oh, this one. Okay, so this is what I'm going to tell you today. I'm going to start from the basic thing like reflection principle, and then how to construct the propagator into standard way, and talking about integrability in the context of multidimensional consistency, which is actually, I believe that you know more or less from at the beginning of the day, right, about this notion of multidimensional consistency here. And I'm going to talk about, well, Lagrangian one form and its quotient relation, and then the main topic is I'm going to give you a multi-term propagator for the continuous case, right? And then I'm going to give you from that new object, we're going to give you a criteria for the integrability, and then I give you a summary. All right. Okay. Sorry. All right. So this from the standard mechanics, you know that actually you have a system, you have a what we call configuration space, right? And so you your system will go from the first point to the second point on that space, which actually we're going to follow a part that we call classical part, right? That which actually that part is give us actually we can find that part with the critical condition of the action, right? And then we get what we know actually the Euler-Lagrangian equation. Okay, that is a very basic thing in this context, which is actually classical. We have only one true part connect between the two different points on this configuration space. But when we move to the quantum level, I think well, we have here the new object, which actually we call the propagator here, which is actually you can construct the propagator from the time evolution operator, right? And so in the quadratic Hamiltonian, I would say, so we can derive actually your propagator can be expressed in that this form, okay? This is a fancy D, which is nothing that you have to take in all possible parts that actually start from this point to that point. That's it. Okay. Right. That we have to keep in mind that actually you can explain your we can explain the propagator in this way at least as well. In the case only of the quadratic Hamiltonian, right? That is the thing. And so, well, next, so I'm going to talk about the standard notion of the integrability. You know, we call that the Yoo-Kong theorem, right? So in this context, if we have a Hamiltonian system, and we can find a set of invariants, right, which is actually in evolution and independent to each other, right? And there must exist a set of action angle variable, right? And then with this existence of set of action angle variable, you can say that your system can be solved, right, by quadrature. This means that your system is integrable, right? Yeah. And so the main feature in this context we call the Hamiltonian commuting flows, right? Okay. So normally we're going to treat this set of invariants as a set of Hamiltonians here, right? And we knew that this we call Hamiltonian hierarchy equipped with this property that actually coming from this one, right, in evolution here, right? And so if we in the standard structure, we know that actually the Hamiltonian is like a time generator. If you have this function that I call dot actually defined on this cotangent bundle, right? And then if you compute the Poisson bracket between this object and with the Hamiltonian, you will get the time derivative with the object right here. Then in the context of multi-time, then here we're going to have more or less the same, but we have, well, if this f is a function actually defined on this cotangent bundle here, and then we can find that actually we have these two equations, and then we can find the second derivative, right? And then we find the difference of these two quantities, right? And then we turn out that actually at the end, after we apply the Jacobi identity, we get this quantity that actually involution, right, of the Hamiltonians. Then we get that actually the order of the time evolution doesn't matter in this case, right here. And so in the well, in the context, if you would like to express this whole thing in terms of the Hamiltonian vector field, right? You're going to you can express things in this way. So it means that so this whole quantity here, the equation here is nothing but this relation. I mean the bracket of the different Hamiltonian vector field acting on this function equal to 0. It means that so if you look at on this cotangent bundle, if you start from this point, right, it doesn't matter you go this way and up, it's going to be the same that you go this way and go to this one. It means that you complete your parallelogram in this sense. So, right. Okay, so now we move to the context of the Lagrangians. Okay, so well, previously I gave you that actually we have a set of Hamiltonians, right? And it means that it must be a set of Lagrangian associated with that set of Hamiltonian, which is actually this one. Technically, we can solve this Lagrangian by apply the not the standard Lagrangian transformation, but a bit tricky one. Okay, and so now the action functional can be written in this form, which is actually this fancy L is nothing but the one form Lagrangian one, and this gamma is a part defined on space of time variable. Okay, and so well so we're going to look at the critical condition on this action, which is actually we have two layers. So if we impose this condition on the space of time variable, we're going to get this quantity to form object here, which is nothing but the Cauchy Lagrange one form Cauchy relation here. But in another layer, you're going to get the what we call generalized Euler-Lagrange equation, but I haven't put here. Okay. So it means that so with having this the Cauchy relation, it means that on the space of time variable here, you can take any part actually from the beginning to the end. It doesn't matter your action is invariant, right? That is the thing. Okay. And so, well, I give you this very important example of the integrable system called Colosio-Moser system, which is the one that I did study for my PhD and construct the Lagrangian multiform, one form structure from this particular system. But the point is that if you look at this hierarchy of the Hamiltonian carefully, you're going to see that the first one is just total momentum, and the second one is the standard one, right? The quadratic of the P, and beyond the second one, then you are not in the realm of the quadratic anymore. So you get P cubed here, and then you keep going further, and you get higher power of the P. Then the question is that how to, well, if you want to construct the propagator, that might be a bit tricky. Okay, anyway, with this Hamiltonian, we have also a set of Lagrangian, which is actually, when I did derive this set of Lagrangian, I did derive it from the KDB system, I believe, and then we perform the quantum limit, and then we get this set of Lagrangian, and later we realized that actually we can construct what we call a Lagrange transformation for the one form Lagrangian transformation here, and then we get a set of this Lagrangian here. All right, and then again, so well the first one we don't have the Lagrangian for the first one because the first Hamiltonian we cannot apply the Lagrangian transformation, right? Because it's not applicable. Then we start with the second one here. This is actually the standard one, and this is and the third one is look very messy here. Anyway, we have this. So as and you probably see in the morning, Frank mentioned that actually he proposed this kind of new object with the propagator here 10 years ago, I believe, at Newton Institute. Okay. Actually, with this new structure of the Lagrangian one form, sorry, we the propagator that we should have, it should take not only possible for the spatial part, but also for the temporal part as well. And I believe that it means that so dependent and independent variables are treated on same equal footing, which is, correct me if I'm wrong, this idea more or less related to the one that actually the overlay given in this year, because he tried to generalize the idea that actually try to treat Q and T on the same equal footing. Then he introduced a new variable, a new parameterized variable right here, and then he got a new set of variable is called X, and which is actually nothing but the Q and T. And by doing this, his action will become this one, and then the Lagrangian standard one going to be this one. And later at the end, he end up with this kind of thing. We're going to have to taking care of the possible of the Q and all possible of the time as well, and in this way. And so, and later, the work by Stephen and Frank again for the discrete KdV, and they impose the periodic reduction, which is actually, you heard a little bit about this from Jacob talk in the morning, I believe, and then they end up with this kind of two discrete time harmonic oscillator, and then they can show that actually with the discrete propagator that they got here, they possess the part independent feature, which actually they call this feature like the top of thing on the standard variational principle. They call it, this is quantum version of the variational principle. Okay, and from this work, what we did try to do is to try to extend the idea to the continuous case. Okay, so first I give you a definition of the multi-time propagator for the continuous case here. So here is Lagrangian one form, and we have also introduced actually the S, which is actually parameterized time parameterized variable, right? And then we can find out that actually for this the multi-time propagator can be written in this way. And so actually this whole thing did a bit is not look like what Frank proposed, because we don't have that kind of separate between Q and T, but I think they are share more or less the same, because we have to take care all possible part of the Q and T as well in this fancy D here. Okay, so let me give you this is definition of the fancy D, which it actually look a little bit mess, not really a bit, but very mess. but I think I'm going to show you for the simple case how to derive this fancy D here. So we start with the 2D space here. It's G1, G2, right here. And so we say that actually if we consider the part, actually the horizontal part here, we can write a propagator in this way. We can do the same for the vertical part here. And so first we're going to consider the part in this configuration, which I call gamma, which belong to this B fancy one right here. And you can see that actually the propagator in this situation is nothing but the propagator from this point to this point, and then you have to integrate this corner point, and you go up there, then you have, this is a corner point here, right? And then this is all the propagator that we have here. And so, but we can simply rewritten all whole thing into this way. That actually this whole bunch of thing here can be put simply in this this gamma actually belong to B1. And this B1 actually there is only one configuration in this in this case, okay? And so next we're going to consider which is actually this type of part in 2D space, which actually, again, I call gamma. Yeah, but I say that this gamma belong to a new kind of new family they call B2 here. Why is that? Because actually you can move the vertical line here from this side and to this side, right? It means that if you move this vertical line from to the right up to this boundary, you're going to get K1 previously, right? But for at arbitrary point here in 1, 0 here, you're going to have extra term that's coming out here, right? And so again, we find out that actually we can simplify this whole thing together, which is actually we can put this into just single equation and say that actually now gamma is belong to the family of B1 and B2 now, all right? Because the first term, as I mentioned, sorry. As I mentioned, the first term is nothing but the K1, right? And yeah, that is the reason why we can compact it, compactify it, and then make it shorter. And so we keep going with a bit more complicated structure here, right? And again, I can call gamma here is actually a new type of part that actually belong to this set of a new family of B3 here. And so we can write out the propagator in this situation, which is actually we have 3 terms. I believe the first one, the second one, and the third one. Okay. And so again, by doing the same trick, we can simplify this whole complicated thing into this very shorter one, I believe. Okay. And then we say that the part that actually we consider now is belong to the B1, B2, and B3. All right. By keep doing this, we're going to have much more complicated equations, I believe. And then, but we're going to find the way actually there's some kind of structure that we can simplify it, and then at the end, so you go like K5 and this one, and then at the end you're going to have I call K all possible part actually. This gamma, it belongs to all possible family of the B in this 2D space here. And we put this n back to make sure that our propagator is normalized, right? In the case of we have to satisfy the probability condition. Okay, is it's not finished yet because what we did is just a halfway. Because what we did is we did start to progress the time in the T1 first, right? And then go up in the T2. Actually, we can do the same trick with if we start with the T2 right here and then go to the right to this point. It means that we're going to get more or less the same with it. You can interchange just T1 and T2, and then you will get a complete of the D in this situation. This means that you have to add another term that coming from the D2 one. Okay. All right. So this is what we had in 2D case space. Okay. For the definition of this fancy D. So what we did here is that actually we're trying to put infinity into infinity because the standard notion of the fancy D contain infinity already, right? But the way that we did the way that we did to construct this all possible part on the time space that we try to put put all possible part in all possible infinity again into this context. I'm not sure that you get this, okay, but and that is the way that we did actually. And so, okay, then so with actually, you know that actually with this normally with this structure of the propagator, we cannot do anything because it's we need to apply the semi-classical approximation, right? To get in order to get the exact form of the propagator, right? So then is that what we did next here? So we consider well, we put our propagator back into the single term with the variable s here, and then we perform the semi-classical approximation right here, and this Q is nothing but the fluctuation around the classical part here. And if you look if you look at this carefully, this Q is in the quadratic form, then you can integrate out exactly, right? And so if you look at this carefully again, this trick is also mentioned in the Andrew talk when he did try to construct his partition function, right? That actually involved with this Lagrangian business here. Anyway, then we're going to look at this particular part actually, and then what is the Q look like. So if you look at this carefully, the Q can be expressed in this way, which is actually more or less with the standard form that we had, but well, it's contained multi-term here. All right. Okay, so now we're going to look at the condition for integrability. So we have a theorem here. So again, so we say that with this set of Lagrangian one form actually satisfy the Cauchy relation. All right, so the propagator for this kind of blue part has to be identity, right? It means that is for the loop part, it does not contribute to the propagator for the evolution of your system. Okay, right. So now we're going to give you a proof. We're going to start to prove by recalling this relation that I call K gamma here, which is gamma is the part that connect between 2 points on the space of time, right here. And we know that actually this Q gamma can be written in this way. And we have another part which is actually sharing the same endpoints, all right? And so we have this one, and then we have Q gamma prime here. And we know that with the closure relation, the difference between these two, then we get we return the difference between these two actions in this way, which is nothing but the closure relation. Then well, we get there is no difference of the action. Then it means that since there is no difference of the action, this means that this Q gamma and Q gamma prime must be the same. It means that your propagator is the same for the gamma and gamma prime. That is the thing. So it means that for the loop one, so you're going to get the identity, right? So next, this is for the loop part. Actually, we're going to consider this the whole object here, which is this is called the loop one. And so actually look a bit, this is nothing but the Q, actually, two Q together. And this is for the loop integration. And so because we have a path independent feature, right? If you look at this, you can try to rewrite this whole thing in this way, and it turns out that actually can be put in this simple form. And once you put this whole thing back into this exponential here, you're going to get the Dirac delta equation, Dirac delta function. And it turned out that actually integrate of the Dirac delta function give you nothing but identity. Yeah, then that is finished the proof, actually. Okay, this is look a bit abstract. Let me give you a concrete example that we can do. This I recall again the result from Stephen and Frank papers. Actually, these two time harmonic oscillators. Yeah? And so the quantity that we're going to compute is the exponential is this whole term actually in the Q function right here, which should actually involve the fluctuation from the classical part here, the y here, which it can be rewritten in this form for this particular systems. And this means that for the Q gamma in this system can be put in this way, all right? And so what we're going to do next is we do the integrating by parts, and we get this one, and then so we're going to start by looking at this part we call gamma A. This part, then we can say that actually this fluctuation can be put in this form because this can be because this satisfies the boundary condition, right? If you put the boundary condition, it's going to satisfy, and then you say you can find that actually they also possess a orthogonal property here as well. And then one you have this one, and you put this y into the Q gamma. You can compute the Q gamma in the Q gamma can be reduced to be very simple form in this way here. And next we're going to consider a part gamma B. We should actually go out first and then go to the right, okay? And for this part again, fortunately, they share still this we can still use the same y that we used previously because they do share the same boundary condition, right? And then again, when you put this y into the Q gamma function, you get exactly the same with the gamma B, gamma A. That is the thing. All right, and then so next we're going to consider a much more complicated, a bit more complicated part they call gamma C here, which is actually the fluctuation can be expressed in this way actually. And then anyway, when you put this y into the Q function, it turns out that actually you get exactly the same with the gamma A and gamma B right here. So it means that so now with this different type of part on the space of time, you have the same Q function or the fluctuation here, and also the same action. It means that your propagator is path independent somehow on this one, possess the path independent feature. Okay, and that's it. And so let me give you a summarize. So what we have here is a kind of a new feature that actually Frank called a quantum variation, kind of on top of feature from the standard variation, right? Because we have a set that they call a space of Lagrangian that we have some, there must be a kind of special set of Lagrangian that play a role for the critical propagator that, and then make the your propagator possess a path independent feature somehow. Okay, and so, and then find out that actually we have the same for the same in the discrete case here. They found that actually the loop path does not contribute to the path. We also find the same, exactly the same for the continuous case, that actually the loop path does not contribute here. And so what about beyond the quadratic case? This is my speculation. From this paper, it seems there might be a way to do the integration beyond the quadratic one. And then I would say that this means that there might be a way that we can construct the propagator, which is actually from beyond the quadratic one, but this density might be different from the standard one. That is the thing. That's all of my talk. Thank you very much.